Hi, good morning, good afternoon, perhaps good evening. It's my pleasure to be here today to participate in the session on reinforcement learning for the Deep Learning Day at KDD 2020. My name is Joelle Pineau. I'm a faculty member at McGill University, as well as managing director at Facebook AI Research. The work that I'm going to share with you today is actually mostly work that I've done at McGill University with some of my students, lessons that we've learned, explored over the years on how to build deep learning systems, in particular deep reinforcement learning systems, towards the aim of having algorithms, implementations that are reproducible, reusable, and robust. I'm assuming most people joining us for this session are familiar with reinforcement learning. Perhaps you've read a version of the Sutton-Barto textbook, perhaps attended some of the many excellent lectures online. Let me just sum up quickly the framework in which we're working when we're in reinforcement learning. The assumption is that we have a learning agent that is acting in a dynamic environment, as opposed to supervised learning where the data is received in a passive way. In this case, the agent has the ability to take actions in the world. It has the ability to observe information from the world. That information is typically captured in a summary that we call the state. It also has the ability to receive information about reward function. That reward is usually an indicator of how good the choice of action was in the state of the system. Over time, through trial and error, trying different actions, the agent evolves a strategy, often called a policy for picking actions. And this strategy determines essentially the behavior of the agent in a test scenario. And so one of the beautiful things about this framework is that it's incredibly general. It can actually capture a large variety of learning scenarios, and it's been used as such for many years. Most recently, over the last 5 years or so, we've seen really impressive results of applying reinforcement learning in domains such as game. And around 1996, a system by DeepMind Google produced a system that was able to play Go at a level far exceeding the best human players. A couple of years later, a system called Robustness, in this case in the game of poker, again showed the ability of our algorithms trained using reinforcement learning to compete with the best human players. And if perhaps you don't care so much about games such as Go, poker, and others, there's actually an impressive number of other applications of reinforcement learning that go beyond this. If you go through the literature recently, you see very diverse application, of course, from robotics and video games, which are perhaps more traditional ones, to using reinforcement learning to design conversational system, to design strategies for medical intervention, eventually to manage natural resources, be it crops, be it animal species, even forest fires, and so on and so on. And so one of the great things from that diversity and that explosion of application is that over time, through all of this work, we're actually learning more and more how to apply reinforcement learning in a way that's reliable, that's reproducible, and hopefully that generalizes across several of these fields. One of the applications where we've done quite a bit of work in my own lab is through the use of adaptive neurostimulation devices. These devices are actually built for patients who suffer from epilepsy. When patients suffer from epilepsy, there's actually an imbalance in their neural activity, such that over time, a set of neurons are recruited to fire synchronously. And the neurostimulation device, which is typically implanted often in the chest cavity and has electrodes running into the brain, both recording electrodes and stimulating electrode. In this case, the role of that device is actually to disrupt the synchronization of the neurons such that the epileptic seizure can't occur. And so by delivering electrical stimulation to the brain, it's actually forcing some neurons to fire, and in doing so, it really reduces their ability to synchronize their firing patterns. The insight of using reinforcement learning in the context of neurostimulation is that you can actually train a computer algorithm to improve the patterns, in particular the timing of the neurostimulation delivery, such as to further reduce the incidence of seizures and, of course, minimize the incidence of stimulation. And so we've done some work on this. I won't go into detail in this particular project today, but we've done some work on this specifically with animal models of epilepsy. And as you can imagine, training a system to perform well with neurostimulation in vitro poses challenges that are quite different from systems that are trained to play Go, poker, or some other games. One of the particular challenge is really the difficulty in collecting large amounts of data. And so if we think more generally, what's the challenge for moving to domains such as games, where you can do a lot of the training in simulation, and it's easy to implement an emulation of the domain, compared to doing reinforcement learning in real-world systems, such as our neurostimulation environment, other medical applications, or some of the other applications I mentioned earlier. One of the primary challenges is the need to be able to learn from relatively few trials. In simulation, if you look in the literature, it's not rare for RL systems to be trained from hundreds of thousands of actions and interactions with the domain, which of course is not a problem if you're applying on a computer system. In particular, you can even distribute this across several computers. When we move to the real world, we sometimes have to contend and learn as best as we can from dozens or hundreds of trials. So in many cases, we don't have the ability to thoroughly explore the whole space of possible algorithms. We don't have the same flexibility to explore the space of hyperparameters and configurations that would be better suited to our domain. We really have to trust that results from the literature will transfer readily to these domains and come up with a solution relatively quickly, given the small amount of data available. And so when we try to solve a problem like that, it's not uncommon to look through the literature for inspiration, ideas, algorithms that might be suitable for the problem at hand. This is a quick survey of papers in reinforcement learning over the last 25 years or so. What you quickly notice, perhaps not surprisingly if you've been following the trends in machine learning, is the really fast rise of these papers. What we're dealing with here is not just the last year of papers where 20,000 papers or so have been published, but it's actually the area over the curve here, noticing that you have many, many more thousands of papers published. And so for someone seeking to take the best findings from the literature and apply them to a new application, this is a pretty daunting task. And so this is why this issue of reproducibility, which I'm discussing, is at the heart of my talk today, is really quite important in this particular scenario. When we talk about deep reinforcement learning, not just general reinforcement learning, there's a few flavors of this. Perhaps the most familiar one is the work on DeepQ network, which appeared in 2015. In this particular case, a neural network was used to process a high-dimensional state representation. So in this case, the agent was mostly focused on playing the Atari games using an emulator, and the observation was composed of an image with several pixels. And so rather than represent the state directly in the pixel space, a convolutional neural net, a very common deep learning techniques for dealing with images, was applied to extract high-level features from this image. And now the strategy for picking actions, and in particular the value of each action, represented here by a Q function, was represented in the state space of, so the last layer representation of this DeepQ network. And there's a number of important subtleties of how to train this particular type of algorithm, which I'm not going to go into today, but if you were to venture in this space, I certainly encourage you to read the literature in doing that. But my point for today is really just to say, of course, acknowledge that there's a class of these deep learning methods for reinforcement learning that are based on using a neural network to represent the state and the value function. A second class of algorithms, which will be mostly the focus of my talk today, is actually an alternate representation where, in this case, the neural network is used directly to capture the policy of the agent. And so we assume, as in standard reinforcement learning framework, that there's a state that is observed. That state is fed into a neural network, and the output of the neural network in this case is actually an action, a probability of an action. And the probability of that action determines the policy that the agent should take. And so this kind of framework can be trained with standard backpropagation. The loss function we use for this is a little bit different than a classic neural network loss function. but nonetheless, it's not very different in terms of some of the underlying deep learning architectures. Now, within this family, and I've given you sort of the cartoon version here of policy gradient algorithms, but within this family of algorithms, there's a few baselines that have become quite prominent in the field over the last years, all of which are actually really good candidates for practical applications and have been used repeatedly in many different applications, as well as many different research projects. And so I've listed a few of them here just to give you an example of some of these standards in the field, but all of them have roughly that same flavor of deep learning. Now, back to the core message of my talk today. I said I would talk about reproducibility, reusability, robustness, and the reason I sort of did this preamble on reinforcement learning is really to situate you in the space. But what I will bring you on next in the talk is really a journey in trying to figure out whether we have achieved high level of reproducibility specifically for this class of deep reinforcement learning algorithms, that is policy gradient methods. So before I go any further, perhaps you may be wondering what's the thread that ties these three concepts together: reproducibility, reusability, robustness. And rather than create it myself, I think this quote for the National Science Foundation actually clarifies this in quite a good way, which is the following: reproducibility refers to the ability of a researcher to duplicate the results of a prior study using the same materials as were used by the original investigator. And reproducibility is the minimum necessary condition for a finding to be believable and informative. And so, of course, when you try to think through this concept of reproducibility in the context of deep learning, it may not take you long to realize that there's actually a large number of sources of experimental variation that can be found in any deep learning, and deep reinforcement learning is not exempt from that. And so I'm assuming most of you are familiar with basic deep learning methods, training of neural networks. And so you will quickly recognize that each of the steps outlined here, going from how did we acquire the data, how did we process it to present it to the network, what architecture was used, and what were some of the hyperparameter specifications from learning weights from initial weights to learning rates and so on, has a deep impact on the results, on the learning of that network. And so how to guarantee reproducibility in the context when there's so many sources of experimental variation actually continues to be a challenge. Specifically for deep reinforcement learning and the category of policy search algorithms I introduced earlier, we performed some experiments to see which of these algorithms actually perform quite well. And so let me give you just a quick taste of some of these experiments. We consider the 4 policy gradient algorithms I listed earlier. It doesn't matter really for this result which is which. We'll quickly understand why. Out of these 4 algorithms, we applied them on a class of benchmarks from reinforcement learning called the Majoko domain. And so the Majoko is actually a set of different tasks where you have these small animated, I'll play the video again for you, these small animated figurines learning to control the joints to achieve a particular behavior. So the one shown here is what we call the half cheetah. I'll let you look at it running again. It's a half cheetah because you get just kind of the half of the animal, a front leg and a back leg. And the goal of using reinforcement learning is to train the control on the joints of that cheetah so they can actually run in a pretty fluid motion. So what we see here is actually a pretty good policy compared to before the training. And if we try out the 4 algorithms I presented earlier on this half cheetah domain, what you observe is that the red algorithm performs better than the other 3 algorithms. Now that may lead you to believe that that's just a superior algorithm. And when it comes to then taking, a choice between these algorithms and applying them in a real world, whether it be for neurostimulation or another application, you would be tempted to think that the red algorithm is the one to go with. It's giving superior results in this benchmark. This benchmark has been well studied, and therefore this would be a useful result. Now, you do notice that the red algorithm has quite a large variance in the results, and so you may be tempted to say, well, let's look at a couple other benchmarks. and see how it does. And so if you do that, in this case, I'm considering two other domains from the same class of these Majoko, the hopper environment where you have a system learning to sort of hop around, and then a swimmer environment where there's a similarly simple agent that learns to swim around. Things look a little bit different. So on hopper, actually the red algorithm is by far the worst of them, barely learning very, very slowly compared to the blue and the orange. The blue is the best, but by a small margin compared to the orange. If you look in the swimmer domain, in expectation, the blue is much better than any of the other ones, but has a really large margin of variance. And so it's really hard to know from these three benchmarks what to conclude, which of these algorithms is actually more robust. And furthermore, these three domains are much more similar to each other than they are to neurostimulation or to most other real-world domains. So it makes it quite difficult to draw conclusions from results presented in the literature to know how to build real-world applications. Now, all of the work that I showed so far is based on open source implementations. And over the years, this movement towards open sourcing code, in particular when releasing paper, has really seen a lot of growth in the machine learning community. In general, I'm incredibly enthusiastic to see this movement and this strong commitment towards open science. But of course, as you probably suspect, the quality of the code is not always the same. And so based on the results I showed in the previous slide, we went digging on the hypothesis that perhaps the implementation we had been using for TRPO was not the best one out there, and that maybe an alternative would be better. And in fact, there's a large number of these implementations that are available. So we picked 3 different ones, excuse me, from the web, and repeated the experiment. Now this is just the half cheetah. And from these 3 different implementations of the same algorithm, we actually see a large gap in performance. And we thought maybe it's just TRPO itself, which is actually quite difficult to implement. And so we started looking at one of the other algorithms, in this case DDPG, and we did it for a few of them. Again, drawing on a few open source code bases to run the experiment. And what you see really is large differences in the results for either of these algorithms based on the Codebase implementation. That was a little bit puzzling to us. And so we started digging into what might be the source of variation. We had some hypotheses, of course. I showed to you already a list of what some of these factors may be that underlie the variation in the results. And indeed, we found that in deep reinforcement learning, as in more classical supervised deep learning, several of the hyperparameter configuration can actually yield a large difference in the results. So we started playing with the structure of the policy network. I showed you early on this policy network and argued that a neural network here could learn the policy, the probability of each of the actions. So we see indeed that has a large impact on the results. We looked at the activation function that goes inside each of the neurons that also can have a reasonably large effect on the results. We then played with a few of the factors that are more specific to reinforcement learning, including the scaling of the reward. It's quite normal to rescale the reward function, perhaps normalize it. And so we do see a large effect of that, whether or not you're applying layer-wise normalization to your neural network. And what's perhaps most daunting is the fact that, of course, there's a very intricate interplay between these hyperparameters. So it's not always possible to, in isolation, optimize each of these hyperparameters. When you're in a setting such as the one I described for neurostimulation, the amount of data you have is incredibly limited. I mentioned a few dozen or a few hundred examples. In our case, we had just a few hours of recordings from which to learn the policy. And so one of the difficulties is to perform that optimization very, very quickly. The other difficulty is that when we look and draw the results from the literature, often, each new paper is proposing a new algorithm. It compares to some baseline algorithms, and it's hypothetically possible that the authors of the paper did not have exactly the same motivation for really finding the best possible solution for the baseline solution compared to their own algorithms. So this positive bias may be playing into the results also. And when we have to interpret these results to make some design choices for our new application, it becomes very difficult to know what to trust. At a high level, it seems like having a fair comparison between algorithms should be easy. Give all your algorithms the same amount of data, same amount of computation, and you should have the same results. In practice, that doesn't always give you the results that you expect. And so this is the result of one experiment that some of my students conducted reasonably late into this investigation. We had controlled for many possible factors of variation in our experimental procedure, really trying to zoom in on having reproducible pipeline. And they came into my office one day with this particular result saying, hey, we've actually run 2 different approaches. We ran 5 different random seeds of each, retraining from the beginning, and we get this results, which seem to show a meaningful effect between these 2 curves. There's just one thing that's a little bit puzzling about this result. Then they revealed both of them were actually the TRPO algorithm with the same code base. And in both cases, they had optimized the hyperparameter configuration of the deep learning system. And so that caused us a lot of pause and trying to understand really, what is going on here. We knew there was some difficulty in terms of having stable and reproducible results in reinforcement learning, but that one stumped us in particular. And so we went back and I said, well, maybe running 5 experiments is really not enough to draw a conclusion. When you want to have a result, usually you plot the average return. That's usually the dark line in most of my graphs. And then you have a 95% confidence interval. That's the shaded version that we show here. The only question that remains really is, how do we pick n, right? The number of experiments. And in this case, each separate experiment corresponds to, rerunning the full training procedure. We're really looking for stability over that training pipeline. And so we started looking in the literature, what's a standard number of n? We thought 5 was not uncommon in the literature, and looking at several papers in reinforcement learning from the last few years, we noticed the following, right? Most of them are doing anywhere from 2 to 9 trials. In this case, most, except for one exception, which depending on the domain did between 3 and 9, 5 seems to be about the most that anyone does. And so we thought that's on the basis of this, that we had done 5 experiments. We did notice one thing, though, that a few of the papers were adopting the strategy where they were reporting what they called top 2, top 3, or top 5 results. And what that seemed to correspond to is actually running a number of full runs of training and testing, and selecting which of the training runs actually gave you the better performance. That seemed a little bit problematic, and let me show you specifically what happens when you do that, right? If you're trying to consider a new algorithm, these are all these squiggly lines I'm showing here. I'm running 10 different random seeds. So 10 times I have reinitialized my weights and done all of the training pipeline, and then tested my final policy. And I'm showing the performance of that final policy as a function of the training number of iterations, so the number of interactions the system has seen. And what you see when you report results from all 10 trials compared to my baseline, you see that there's a reasonable amount of variance. Perhaps here you would conclude that it's impossible to tell whether the new algorithm is actually better than the baseline. If I were to report, however, just the top 3 results from those 10, here's what it would look like. And so 2 things happen in this case, right? First, there's a very strong positive bias. It seems to be the baseline. And second, the variance appears much smaller. And so unfortunately for us as a community in deep reinforcement learning, this kind of practice of reporting top K results has crept in slowly. And these things can be reasonably insidious. A few papers do it. And then everyone has to do it to have results that are comparable. And if you don't do it, it becomes very, very difficult to have comparable results. Nonetheless, I'm not here to advocate this kind of reporting of results. If anything, I'm really here to share with you different dimensions that are useful when you're reading the deep reinforcement literature to sort of, keep some really keep a high level of awareness so that you can piece through how the results are presented. Now, having discovered that, we share these results with a few people in the field, and at the same time, a few other results appeared also suggesting some difficulty with experimental work in deep reinforcement learning. I would be quite sad and feel I hadn't done my job today if you leave this session believing that's the state of affairs in reinforcement learning. In fact, I think this was really just an opportunity. These kinds of results and that of others was really just an opportunity to take an honest look in the mirror and ask ourselves, is it quite so simple in terms of having fair comparisons? It may be necessary in some cases to have a much more nuanced understanding of how the experimental results are obtained so that we can actually draw robust conclusions about the work. And some of the findings we have related to this show that, in fact, different methods may have different distinct sets of hyperparameters, may necessitate different budgets in order to be properly validated. And so in this space, I showed you earlier this graph with this ever-increasing number of papers, quite daunting, how quickly the field is moving, the literature is. I shared with you a few results, perhaps raising alarms about how generalizable were the finding in those papers, how much you could hope to take this knowledge from the paper and actually apply it to new domains. I don't want to leave us on there. Beyond this, we tried to see whether these patterns were reflective of the whole field and whether there were things in papers that could give us an indication of reliability and potentially reproducibility. So we surveyed 50 reinforcement learning papers from 2018 that were published at some of the top conferences in the field, at least the conferences which see the most volume of such work. And from those papers, 100% of them had experiments, and so that was an inclusion criteria for this little survey of ours. Not only that, 90% of them used neural networks, also again focusing really narrowly on deep reinforcement learning. 90% of them described all the hyperparameters for the algorithms they were proposing. 60% of them only described all the parameters for the baselines they were comparing to. So you can think of baselines here as being alternate previous algorithms, and the performance of the new proposed algorithm is established in comparison to these baseline. 55% of papers had a link to code. Now, I suspect this would have improved if we were looking at papers from 2019 or even 2020. We've seen really a steady increase in the field on the use of, or on the sharing of code with papers. But at the time, 50% of them had code linked. 20% only were specific about what method they used to choose the hyperparameters. 10% of them only did some evaluation on a held out test set. And only 5% of them actually applied significant testing before presenting the results. And when I talk about having proper estimation done on a holdout test set and significant testing, I'm not really talking about graphs of this kind. Many of them had graphs of this kind, but in many cases, they did not properly define the type of uncertainty that was presented, whether it was variance, confidence interval, and if so, what type of confidence interval. So still a lot of work to be done in 2018. Since then, we've been really into building tools and practices that help the community come along and improve their practices in this respect, in particular with experimental methodology. So, what can we do? In fact, let me share with you a few of the recent developments in the field, and perhaps they can inspire you whether or not you're doing deep reinforcement learning, because quite honestly, the solutions are not that specific to reinforcement learning, though this is a field that particularly was crying out for them. So looking for inspiration to help our community perform better, we went, on a wide investigation trying to get different ideas. And in particular, we looked at cases where there was really a high level of safety necessary. And so, when you talk about flying a plane or performing surgery, two domains where clearly the stakes are very high, and the communities have spent a lot of time thinking about how do we develop tools to make sure that we perform at the best of our abilities. And so one of these tools that has proven remarkably successful is a simple checklist. Both in surgery as well as for planes, it's now absolutely common practice to go run through a checklist, safety checklist, before getting started, to make sure that no trivial element is forgotten. And this has shown demonstrably an improvement in the safety. And so in an attempt to help our community, we've actually developed the machine learning reproducibility checklist. It's available openly. You just need to look for it on the web. There's a few versions. What I'm showing here is actually the most recent version as of April 2020. There's a few sections to this checklist. It's actually designed to ensure that you have all the components that through our studies we have found were predictive of good reproducibility and robustness in the work. And so this includes, for all the models and algorithms that are presented, a description of the mathematical setting, the assumptions, and ideally the complexity of the algorithm also. If there are theoretical claims accompanying the work, you can include a clear statement of the claim, a complete proof. For any data set that is used, of course, some amount of information is required, including the statistics, how the data was collected, an explanation of any data that might be excluded, a link to a downloadable version of the data set. And if it's a new data set, a description of some of the data collection process. This is only the beginning. There's a second part. In addition to this, for any work that includes shared code, check if you include some specification of the dependencies, training and evaluation code, ideally the pre-trained models, and a README file that is very precise about the commands to run to reproduce the results in the paper. And for specific experimental results, there's a list of items also, the range of hyperparameter considered, how to select them, which in our previous survey was often absent, the hyperparameters used to generate the results, number of training and evaluation runs, specific measure of statistics, central tendency, variation, average runtime, and then finally the computing infrastructure used. So this particular checklist was deeply inspired by the work that we did on deep reinforcement learning, but we actually framed it in a way that is much broader than that, and we believe usable for machine learning at large, and data science even also. Based on this particular reproducibility checklist, there's been actually a lot of sharing with the community and adoption across the community. Before I tell you about that, let me insist on maybe one point that I have overlooked so far, and that is the role of infrastructure on reproducibility. It's well known in several other sciences, including in the medical sciences, that the setting in which the experiment is conducted, whether it be a hospital center or a specific apparatus, can actually have a large impact on the results. In our work in machine learning, often we assume that because we're running on computers, in fact, these are set up to be deterministic machines. Every time you launch the algorithm, it should give you the same results. And I just want to call out as a small parenthesis that as we move more and more towards distributed training system, many computers in parallel computing different aspects of the function, perhaps doing different, collecting different data, especially in the case of deep reinforcement learning. It's not unusual to have several computers simulating different data that then gets fed in the reinforcement learning algorithms. There can be some amount of variation that comes in through the scheduling system that is used to distribute the computation across several computers. So that's something to consider, and that is why we included one of these items in our checklist. How has the checklist or any of our finding been useful? At the NeurIPS conference, which I am assuming many of you are familiar with, both in 2019 and 2020, we crafted a reproducibility program informed by some of our work that was designed to help authors submitting papers to improve the reproducibility of their work. There were three components to this program. The first one is the use of the ML reproducibility checklist on all paper submissions, both at initial submission and also at the final submission stage for accepted papers. There's a code submission policy, which was explicitly specified by the program chairs, encouraging authors to share code of their work along with the paper as an accompanying artifact. We saw a really nice uprise in the number of papers that are accompanied by code, from about 50% at NeurIPS 2018 to actually about 75% at NeurIPS 2019. I haven't seen the numbers yet for NeurIPS 2020, but already the trend was incredibly encouraging. The last component of the reproducibility program was actually a reproducibility challenge. This is an interesting one, which we had piloted at iClear for the 2 weeks previous. I'll tell you about it in a second. For anyone who's interested in full details about this reproducibility program, we have a paper that's available on arXiv that actually gives you a full account of what we tried, as well as an analysis of all the components, including results of surveys from the authors and the program committee. And so for any of you who may be involved in the organization of a conference in the next few years, I encourage you to take a look at this and see if any of the findings there can be useful for you. Finally, let me close by emphasizing one message that I think is important to keep in mind. Too often in our daily lives, you know, we are moving quite quickly, trying to make progress. There's a lot of pressure in how we operate, and it seems like participating in science or academic research is almost like a competitive sport. And part of my message today that I hope you will take home with you is to go back to the foundation of science as really a collective institution, and that our role in this institution is really to help understand and explain phenomenon. And when we do that, really these core components of reproducibility, reusability, robustness are absolutely essential to how we contribute to this institution. And so please don't forget that in the work that you do. I'm going to say a big thank you to all of my collaborators. It's my pleasure to be here sharing this with you today, but actually there are many people who contributed deeply to the work presented here, so I'm pleased to acknowledge them. Thank you very much. That's the end of my talk today, but I hope you enjoy all the other sessions and the rest of the discussion.